don't collapse when large trucks drive over them? Well, the answer is structural engineering. Structural engineers use physics and math to design and analyze the sturdiness of structures. You know, things like bridges, buildings, concert stages, and even roller coasters. Don't get me wrong, designing any one of these things can involve multiple types of engineering, but it's structural engineering that's responsible for making sure that that structure won't collapse or fall over. You see, a structure must be able to handle the forces or loads that it's likely to experience. Take a skyscraper, for example. It not only has to support itself, but also all the people and furniture inside the building, and then external factors like wind, snow, or an earthquake. The materials and geometry that make up a structure influence how it may respond to those forces. Different materials have different properties like strength, weight, and flammability that can influence a structure's sturdiness. For example, steel is generally stronger and weighs more than wood, and different geometric shapes work better for different purposes. For example, a square or rectangular base can typically hold more weight than a triangular base. So structural engineers perform calculations to determine the best materials and shapes to use in order to build a sturdy structure. So the next time you find yourself at the top of a roller coaster, you can thank structural engineers for doing their part to make sure it's nice and sturdy.
All right.
Yeah, so that's that. So,
Yeah.
so a structure is the arrangement and the relation between the parts or elements that make up something complex. So in this example, there is a bunch of blocks and that make up the structure, and then here's the structure. Yeah. So for the topics that we'll be going over, we'll be going over historical structures, material properties, thermal expansion.
Sorry to interrupt for a second, but James, I think your screen is not working.
Yeah, I think I can try sharing mine.
Yeah, I think Justin should share.
So this should work. I'm just in editing mode. Who doesn't go in editing mode? So we'll be covering over historical structures, material properties, thermal expansion, loading scenarios, trusses, dynamic load safety factor, loading, cross sections and stress, forces, and equilibrium. So for our main focus, both tests will focus on the ability to analyze a structure and think about what forces or stresses members are withstanding. So this includes tension, compression, bending, shear, torsion, and buckling. Please note that all of these above are not mutually exclusive. That means it can't happen only once. For example, a bridge might experience both compression and tension instead of only one. Be comfortable with the definitions of the above and the intuitive scenarios of when they occur. So for our first historic structures, we're going to be looking at Greek structures. And an important historical innovation of ancient Greek structure is the use of pillars. Pillars were created by stacking smaller pillars above each other, as you can see here. So the structure remained strong under compression, like pushing down on it, but it was very weak against torsion, like it was being twisted. Another historic structure we're going to be looking at is Roman, and the Roman arch was the foundation of many buildings in that time. So the arches were made of concrete, and the keystone is the most important part of it. It's a wedge-shaped stone at the top of the arch that is set last when building it and holds the rest of the arch together. The arch is strongest under compression or being pushed down because it distributed the weight onto the ground. There are three material properties, which is mechanical, physical, and chemical. So mechanical material properties include strength, toughness, hardness, brittleness, malleability, and ductility. Physical material properties include density and thermal expansion, while chemical material properties have the ability to corrode and have a certain chemical stability. So there's isotropic versus anisotropic. And isotropic is material properties that are independent of direction. For example, aluminum is the same strength in every direction, while anisotropic is material properties that are direction dependent, such as carbon fiber, which the strength depends on the direction you consider and its orientation with the grain of the fibers inside of it. To look more at anisotropic materials, they don't have the same strength when loaded in different directions, which we went over. This includes wood, which is composed of many grains and is only strongest when the grains are in tension or compression. Carbon fiber is composed of fibers glued together with epoxy, and the fibers are strongest in tension only, kind of like fabric. 3D printed materials is composed of stacked layers of plastic, and each individual layer is reasonably strong, but it can be pulled apart easily. So first material property we're going to be looking at is steel. Steel is a alloy of iron that is part carbon to improve the strength and fracture resistance. It's highly recyclable, with steel that is made in the US can be 98% recyclable, more than other construction products. The Bessemer process is allowed for the cheap mass production of steel, which let large-scale projects work because using lots of steel. Steel annealing is a process by heat treating it and it changes its physical properties. So a few types are stress relief, which reduces stress on the steel caused by processes such as forming, straightening, or rolling. Spheroids only works on steel that has more than 0.8% carbon. The process improves the ductility and the toughness of the steel, but it reduces the hardness and its strength. It's generally used on steel that has already been hardened, and so it could be workable again. Another few is normalized, which is only used in ferrous alloys and helps achieve a uniform grain in the alloy. The process of peel softens steel by slowly heating it and slowly cooling it. A full anneal heats up steel to be on its upper critical temperature before being cooled down. For concrete is generally made up of a mix of cement, water, and either stone, gravel, or sand. There's also a binder that's mixed in. Water is required to increase the workability of concrete, although the exact ratio can vary depending on the compressive strength needed from the concrete. The water to cement ratio is between 0.4 and 0.7. Too much water in concrete can lead to the liquid evaporating after the concrete is already set, forming gaps in the concrete which weakens its strength. A rebar or reinforcement bar is a steel bar or wire that runs through the concrete and is used to increase the tensile strength of concrete. Rebar is generally made with an uneven surface to better bond with concrete. Steel has thermal expansion coefficient similar to that of concrete, thus lowering the possibility of additional stresses on the concrete. Poorly designed rebars and placing it incorrectly can lead to structural failure, such as the collapse of the Cypress Street Viaduct in Oakland, California, not too far from me. Depending on the location of the cement, different types of rebars can be used, such as sheet metal, welded wire fabric, stainless steel, and epoxy-coated rebars. Another material property we're going to look at is wood, which can be classified into hardwood and softwood. Hardwoods generally have broad leaves, and softwood have needle-like leaves. Wood is hygroscopic, meaning that the moisture level of wood depends on the humidity of the surrounding air. The fiber saturation point refers to the point in which a piece of wood has no free or excess water. Below this point, wood shrinks as it loses water and swells as it gains water. Wood warping is the uneven drying of wood. and it causes warps and distortions in the wood. If uneven drying happens frequently, it can create separations in the wood called checks. And checks are perpendicular to the growth wings of the wood. It's right here. So I think.
All right, I'll take over from here. So thermal expansion is when materials expand and contract depending on the temperature of their surroundings. The thermal expansion coefficient A sub L describes a ratio change in length per unit temperature change. The units are 1 over Fahrenheit or Fahrenheit to the -1 power, 1 over other units of temperature like C or K or Celsius or Kelvin. If a material had an A sub L equals 0.01 degrees Fahrenheit to the -1st power, it would grow by 1% in length for every degree increase in temperature Fahrenheit if heated uniformly. So as you can see here, here's the equation in the image and then all the variables. All right. Continuing on thermal expansion, assuming the material has a positive A sub L, a material is also going to shrink by the same percentage for a corresponding temperature drop. If a material is unevenly heated, different parts of the material will expand differently and cause stresses within the material as a result. If a material is evenly heated, it undergoes no stresses at all. Materials can still cause stresses from uniform heating if they expand against something, for example, against something else that doesn't want to move. So these are some loading scenarios: compression, tension, shear, bending, and torsion. All right. Compression is when an object is being pushed together. Arches and columns are under compression, and in some scenarios, if a certain beam or column is sufficiently long compared to its cross-sectional area or width, it may buckle before it actually fails in compression. For example, pasta will buckle and then bend until it fractures. As soon as buckling occurs, the structure has failed. Cardboard often buckles when you try to crush it from the ends. Tension is when an object is pulling apart. Cables and ropes are under tension, and the chain supporting a chandelier is also under tension. All the cables in this bridge below are also loaded in tension. So shear is a loading scenario where part of a material is being forced one way, but the other part is being forced another way. This can cause material to break apart along a plane prematurely. Some materials are not as strong in certain directions. For example, wood is resistant to shear loads that avoid the grain plane, but not loads that are parallel to the grain. As you can see here on the right, this bolt was holding two plates of materials together and then deformed under a shear loading. All right, now let's talk about bending. A given beam under bending typically is actually partly loaded in compression and partly loaded under tension. A beam typically fails under a bending load because it exceeds the maximal tensile load or exceeds the maximal compressive load in a given part of the beam. Certain bending scenarios, like 4-point bending, can lead to the beam being loaded in pure internal shear. All right, torsion is a type of loading that tends to cause the material to twist. The highest stress region of a cylinder or beam is the region on the outside, furthest from the rotation axis. Shafts that spin like a drive shaft or an axle are typically loaded under torsion. Torsion from an applied torque causes shear stress on the material. Now let's talk about cross sections. A cross section is like a slice view of an object. For example, the included image is an image of two cross sections of two steel I-beams, as you can see here on the right. And the area contained inside a cross section is called the cross-sectional area. The strength of a given structure or beam is often dependent on its cross section. Stress. Stress is equal to force acting on the cross section over cross-sectional area. So some examples of stress are tensional stress, which is force tension over cross-sectional area, and shear stress, which is shear force over cross-sectional area. As you can see here down in these images. All right, now let's talk about units. A unit of area has dimensions of length squared. So 1 square meter or 1 meter squared is an example of a unit of area. Newtons are a unit of force. 1 Newton is equal to 1 kg over 1 kg times a meters over second squared. Pascals are another unit of stress, are a unit of stress or pressure, and it is a force per unit area. 1 Pascal is 1 Newton per square meter, and 1 psi is 1 pound per square inch. Kilograms are a unit of mass, not of weight. On Earth, 1 kilogram does not exert 1 Newton of force. On Earth, 1 kilogram of mass exerts a weight of 9.81 newtons, since G equals 9.81 meters per second squared. All right, now let's talk about forces and free body diagrams. A free body diagram shows the forces, pictured as arrows here, acting on an object, which is pictured as a dot. All right. As you can see here, there are 4 forces acting on this person that's pushing the box, which is normal force, applied force, gravity, and friction. An object is in equilibrium if the forces are balanced so that there is no net force. This means its horizontal forces balance out and its vertical forces also balance out. So the sum of the forces to the left is also equal to the sum of the forces to the right, and it's the same for up and down. Diagonal forces can be split into their components, which is method. We'll talk about these methods on the next slide. As you can see here in these images below. All right. Now let's talk about triangles. I'm sure many of you, or at least some of you, know about the Pythagorean theorem, which applies for right triangles. A squared plus B squared equals C squared, and A and B are the length of each of the legs of the triangle, and C is equal to the length of the hypotenuse. Now let's talk about trigonometry. Phi is the magnitude of the diagonal force. 36.87 degrees is the angle, and the horizontal component has a magnitude of 5 times cosine 36.87 degrees, which is equal to 4. The vertical component has a magnitude of 5 times sine 36.87 degrees, which is equal to 3. Now let's talk about trusses. Trusses are assemblies of beams connected at joints to form a rigid structure. The earliest known truss dates back to early lake dwellings from the early Bronze Age. For truss problems, make the following assumptions. Pin joints at the end of each member or link, and each member can only experience tension or compression. So solve using method of joints. Each joint must be in equilibrium, which means forces sum to 0, and pick a joint and solve for unknown forces. Now, let's talk about dynamic loads. Not all structures are static. Some structures are meant to move, like a wind turbine or a drawbridge, as you can see here in the image. Even structures that are traditionally static have to undergo dynamic loads such as wind. Now let's talk about safety factors. If a certain part of a structure would only see loads between 600 pounds and 800 pounds, you might not want to design the part to fail at exactly 800 pounds, as it would be very likely to fail in real life. Instead, engineers design parts with a safety factor so that they can withstand the maximal value of the real world load plus some more margin. For example, in the above case, if the part was designed to fail at 1,000 pounds, it would be said to have a safety factor of 1.25, since 1,000 divided by 800 equals 1.25. The formula for the safety factor is maximum load divided by current load. Now let's talk about pressure vessels. Containers that hold in pressure, known as pressure vessels, generally have their walls loaded in tension. The gas or liquid inside is high pressure and wants to expand outwards. This pulls the walls apart, loading them in tension. Balloons and shaken soda bottles are examples of pressure vessels. A pressurized piston is also an example of a pressure vessel. So go to this link to practice what you learned. I'll put the link in the chat. And go to pages 17 to 23 and work on problems 1 through 30. Answers are on page 24. Now, Justin will
Yeah.
Ask some questions.
So before we actually start doing it, we can go over a few. So let me share my screen again. I think you guys can see it. So here are the test questions. And we're gonna start with number 3. So why is rebar generally made with an uneven surface? And you have these options: to adhere better with concrete, to withstand corrosion in areas with high humidity, to keep the manufacturing process simpler and cheaper, and to prevent bending in areas prone to earthquakes. You can put the answer in the chat, and it's fine if you don't answer. So I'll give you about a minute. I think time's up. So the answer is actually A, because in the slides it helps adhere better to the concrete. So the fourth one, we can do this one, which is crushing a long cardboard piece from 2 ends, is an example of tension, torsion, bending, or buckling. You also have a minute for that too. Yeah, so I think time's up, and the answer is D, it is buckling. So we'll actually skip a few. If you're gonna do this work, you can just memorize it. Number 3 is A, number 4 is D. If you're gonna do the homework tonight, you can just remember those. So now we're gonna go over questions 8 and 9. So first we're gonna start with 8. So out of these images right here, labeled A, B, C, D, and E, which of them depicts tension? So the answer is A. It's the first one because tension means an object being pulled apart. You can clearly see it's being pulled apart. For the 9th one now, which one depicts torsion? You have these options, and it's not A. I'll give you a minute for that. I'm just gonna go quickly now. the answer is E because torsion means something being twisted, and E shows that. We're going to skip a few, but just remember if you're doing again, if you're doing this, 8 is A and 9 is E. So we're going to skip again, and we're going to do 11 and 12. So you can see this drawbridge here, or I mean, just a bridge. So we're going to start with number 11. It's what force do the cables of a compression bridge primarily experience? So the cables are the red lines. They're the cables. So you have compression, tension, torsion, or shear. I'll also give you some time for that. So the answer is B, which is tension, because the cables are holding the bridge, and the heavy bridge or the ground area, which is light gray, I think, is pulling on the cables. So for the 12th one, it's asking what about the towers of the bridge? So the green lines here are holding the bridge up, and so what do they experience? Do they experience compression, tension, torsion, or shear? And this one's kind of tricky, so I could give you a hint. It's that the pillars are holding the bridge up. They're holding a lot of weight up. Anyone else going to answer? Okay. I guess the answer is A, which is compression. And it doesn't really look like compression, but since it's holding the bridge up, the top part or the entire thing around the middle where it's holding up the bridge, it's experiencing compression. So, quick recap. 3 is A, 4 is D, 8 is A, and 9 is E. 11 is B, and 12 is A. And if you're doing this, not only do you get that, but there's also the answer key in the back. So, yeah. So, if you have any questions, you can email ejunwu2004@gmail.com.